We're going to prove some trig identities here. Suppose you're asked to prove that the sine of x is the cosine of 90 minus x. Go to a right triangle. Remember, these two angles straight up add up to 90. If this is x, then this must be the other 90. That is, after you used up this 90, you only have 90 left. So everything goes here, all 90, less what you put here. Or can ask yourself, if you have x, what do you add to it to get 90? Well, you have to add 90, so then I have the 90. But I don't want that x. I don't want that x. I know what to do. Let me take away the x. So when you add this and this, you get 90. Now let's just label this, say A, B, and C. The sine of x is equal to the opposite of x divided by the hypotenuse, the cosine of c. It's c, the hypotenuse is c. Now, what is the cosine of 90 minus x? The cosine of this angle. Well, it's adjacent divided by the hypotenuse. The hypotenuse is always opposite the right angle. Ooh, I got the same answer. Look at that. The sine of x is cosine of 90 minus x. Exactly what I was asked to prove. Now, I just want to write that one down. 90 minus x. Well, I claim that the cosine of x is equal to the sine of 90 minus x. Okay? I pick a right triangle. I'll call this x. Since this is 90, the other two angles have to add up to 90. So I have 90 minus what I've already used for that angle up there. I already used x. And if I let me label it the same. If I label it ABC as follows, let's see what I get. The cosine of x is adjacent over hypotenuse. It's b over c. The sine of 90 minus x, the sine of this angle, is opposite, which is b, divided by the hypotenuse. Ooh, they're equal. So yes, this is true. Now, there's another way of proving that one without triangles, so long as you know the first one. We know that the sine of x is the cosine of 90 minus x. Well, suppose I say let u equal 90 minus x. So this piece would therefore be the cosine of u. Now, if I interchange those two letters, I get that x is 90 minus u. Well, I know that the sine of x is equal to the sine of that, but I'm now allowed to write x that way. Just like I was able to write 90 minus x as u, I can write x as 90 minus u. So it's the sine of x, which is 90 minus u. But u is just a dummy variable. I can let u be x, maybe big X, so it doesn't look like the original x. The cosine of an angle is equal to the sine of 90 minus the angle. That's exactly what we set out to prove, and I used the first proof, or the first fact that we derived, to do that. Now, we know that the sine of x is equal to the cosine of 90 minus x. And we know that the cosine of x is equal to the sine of 90 minus x. Well, let's divide the two. The left side is tangent of x. The right side, the angles are both the same. Cosine of an angle divided by the sine of the same angle is the cotangent of 90 minus the angle. So we have this proof. So now, if I call that u, if I let u just like before be 90 minus x, if I switch those, then x is 90 minus u. Okay, so x is 90 minus u, and cotangent of 90 minus x is u. So I get that one. Okay. Let's now do some more standard proofs. Suppose you were asked to prove that sine of x times the cotangent of x is equal to the cosine of x. This side looks simpler than the left side. It's just one trig function. It's not a product of trig functions. So we're going to leave that one alone. We're going to make the more complicated side, the left side, equal the right side. Well, sine x is sine x. So my goal right now is to write everything in terms of sines and cosines. Sine x is already in terms of sines and cosines. Cotangent x is cosine x over sine x. The sine x's cancel, and what do you know? I do get cosine x. This really does equal cosine x. I know, we proved it. Suppose you were asked to prove that the cosine of x times the secant of x divided by the tangent of x is equal to cotangent x. Now, you might realize that if this top was 1 over tangent x is cotangent x. So we really just want to show that that top is 1. So cosine x, secant x over tangent x. Now, since the tan x is in the bottom, and basically this is 1 over tangent x, I'm going to safeguard that. In fact, I might even factor it out. I don't want to lose that for the life of me. So I have 1 over tangent x. Cosine x is cosine x. Secant x is 1 over cosine x. This cancels out. That's 1. So you get 1 over tan x, which is cotangent x. Now, your teacher may tell you, don't change the right-hand side. Nonsense. You can change it and say, oh, I want to get it to look like that. So once I got it to look like that, I immediately said it's cotangent x, and then to make your teacher happy, you could erase that. That is that problem. The next problem. Suppose that you were asked to show that cotan x times secant x over cosecant x is equal to 1. Well, it's doable, but it's going to be hard to change 1 to make it look like the left side. So the right side is easier, so we'll change the left side. All right, everything in terms of sines and cosines. Cotangent x is cosine x over sine x times secant x is 1 over cosine x over cosecant is 1 over sine x. Here we have that canceling. Oh, and we're done. We get 1 over sine x in the numerator, and we have 1 over sine x in the denominator. Those are both the same. You divide them, you get 1. I mean, if you ever have 2/3 over 2/3, do not keep this, change that to multiplication, and flip that over, because you're going to get 1. If you divide the same quantities, and they're not 0, if you divide the same quantities, you get 1. And that's what we set out to show. I mean, if you insisted on going a step further, 1 over sine x is cosecant x over cosecant x, which is 1. You could have chosen to multiply the top and the bottom by sine x. 1 over sine x times sine x is 1. 1 over sine x times sine x is 1. So you get 1. Or you could have done what I suggested you don't do. You keep the top, you change division to multiplication, and then the bottom you flip over. Again, you get 1. Divide the same two quantities, you get 1. Let that be a skill you have. The next problem. Cosine x over secant x sine x. This is equal to cosecant x minus sine x. The left side is just our product. The right side is a subtraction. Sorry, the left side is a fraction. I apologize. The right hand side is a subtraction. And I know that the first term I can write as a fraction. So then once I have a fraction, I can get common denominators. I am going to change. I'm going to work with the right hand side. I know I've been boxing the easier one, so let me continue to do that. The left side looks easier. So I wrote down the right side, there it is, and cosecant is 1 over sine x minus sine x. So I get a common denominator. I divide by sine x, but then I have to multiply by sine x. So now I'm in subtraction. The denominators are the same. I keep it the same, and I get 1 minus sine x times sine x. That is sine x squared. But remember, sine squared x plus cosine squared x is 1. If I bring that to the other side, I get cosine squared x is 1 minus sine squared x. That's cosine squared x over sine x. Then I look at what I want. I have the sine x in the bottom. So I'm going to safeguard that. But you know what? I only want cosine on top. Well, cosine x squared is cosine x times cosine x over the sine x. So that part I want. That's this part. And then I realized, oh, this is simple. And even if I didn't realize this, now I know that cosine in the top has to be secant in the bottom. Even if I didn't know it, now I know it. And I can use that for an earlier problem or a later problem. I now know that cosine x must be 1 over secant x. That is, I put this in the denominator as secant x, and I got exactly what I set out to get. I started with this piece right here, and I concluded it equals this. That is, it equals that. So, that one is done. The next one we'll try to do is sine x plus cosine x times cotangent x is equal to cosecant x. And whether your teacher likes it or not, that's 1 over sine x. Now, this side is nice and simple, or even this. It's just 1 over sine x, or cosecant x. Here we have a sum. That's more complicated. Work with the it's easier to get something complicated to look easier than something easy like this to look more complicated. How on earth are you going to get cosecant x or 1 over sine x to become a sum? I mean, I know one way. The only way I know of is that one is sine squared x plus cosine squared x over sine x. And at least now I have a sum. But that's pushing it too far. So we're going to work on the left side. And the nice thing about the left side is that cotangent x is going to put a sine x in the bottom. Cotangent x is cosine x over sine x. But I'd love to have a common denominator, which means I'm going to multiply this term by sine x over sine x. That way we have the same denominator. Sine x times sine x, that's sine squared x, plus cosine x times cosine x is cosine squared x. And even if you didn't know that this top is 1, it has to be 1. It has to be 1. You say, oh yeah, I remember my teacher saying that sine squared x plus cosine squared x is 1. And 1 over sine x is cosecant x. And erase this because your teacher makes a big deal about you writing on both sides. And there it is. I started off with this, that is this, and I got it to equal that, which is that. That's all I needed to show. Let us try another one. The cosine of negative x plus the sine of negative x is equal to the cosine of x minus the sine of x. Well, the right-hand side is simpler because, the left and the right look very similar, except the left has negative x as the angle. So this is, if I'm not mistaken, our one-step proof. Cosine of negative x is just cosine x. Sine of negative x, the sine comes out in front. So making that addition, subtraction, sine x. And that's what we wanted to show. Know your laws, and sometimes it's easy. 1 minus sine x times 1 plus sine x. This is equal to cosine squared x. I think it's somewhat obvious that the right side is nice and simple. It's just cosine squared x. Left side, not all that complicated looking, but it's a product, and it's a product of sums and differences. It's definitely more complicated than this. But it is this is, I forget what they call it. I know that A minus B, they're conjugates, right? A plus B. I know that that product is the difference of squares. We square A, we square B, we subtract the 2. So this is going to be 1 squared minus B, which is sine x squared. That is, it's 1 minus sine squared x. But that is cosine squared x. Because if you brought that to the other side, you would have 1 is equal to sine squared x plus cosine squared x, which we know is true. So if you bring it back, you get this, which is true. 1 minus sine squared x is cosine squared x. And that is what we were asked to show. Now, suppose you have sine x plus cosine x all squared, and you want to show that it's 1 plus 2 sine x cosine x. Now, I really want to say that that's the hard-looking one. Now, how am I going to get that to be something squared? Now, I can easily get this to be something that isn't squared by squaring it. So, I think we should do that. We should actually square this. So we get the first squared. We get 2 times the first times the second, which is sine x cosine x, plus we get the second squared. And then the problem's over, because this plus that is 1, plus this. Well, that's what they asked me to show. They asked me to prove that this is equal to that. Okay. Now, if you ask how, so we went from here to there. How would you go from there back? Read upwards. Replace 1 with sine squared x plus cosine squared x. This didn't change. And then say, oh, I know what this is. It's sine x plus cosine x all squared. It's easy to see once we proved it in the other direction, but just read it backwards. This is true for all of them. Read it backwards. Cosine squared x is 1 minus sine squared x. 1 minus sine squared x is 1 squared minus sine squared x, which is the difference of squares, which we can write that way, and we're done. I started with cosine squared x, and I got this. You can always read it backwards. Cosine x over secant x plus sine x over cosecant x. I want to show that that's 1. 1 couldn't be any simpler. I'm going to play games with the left-hand side. So cosine x over secant x. Oh, this is very simple. Over sine x over cosecant x. Well, I'm going to bring this to the top. So I have the cosine x on top, but secant in the bottom is cosine on the top, plus the sine x that's on the top. But you know what? Cosecant on the bottom is sine x on the top. So I get cosine squared x plus sine squared x, and that's 1. Now if I read it backwards, I'll even write it. 1 is cosine squared x plus sine squared x. That's from here to here. But that equals this. That is, cosine squared x is cosine x plus sine x sine x. And this cosine x can stay in the top, and that cosine x can go in the bottom as secant x, plus that sine x can stay in the top, and this sine x can go in the bottom as cosecant x. But that's exactly from here to there. Okay? Don't start with 1. I'm just showing that you could. Suppose you were asked to show that sine x over 1 minus cosine x minus cotangent x is equal to cosecant x, which we won't tell anyone, is 1 over sine x. Now, whether you look here or here, that's a lot simpler looking than this. It's not easy to get cosecant x to become a subtraction. It's not easy to get 1 over sine x to become a subtraction. I would start with the left-hand side. Like I said, it's easier, usually, it's easier to get something complicated looking to look easier. It's called simplification. I'm not going to touch the first fraction, but this is cosine x over sine x. I want to get common denominators. It's going to be sine x times 1 minus cosine x, which is good because I want sine x to be on the bottom. In the first fraction, I need to multiply top and bottom by sine x. In the second fraction, I need to multiply top and bottom by 1 minus cosine x. So I have the denominators, this times this, minus this times this. They're the same denominators. I wrote them down. The numerator is going to be sine x times sine x, which is sine squared x, minus cosine x times 1, which is cosine x. Cosine x times minus cosine x, which is minus cosine squared x, and sine squared x minus negative cosine squared x, that's sine squared x plus cosine squared x, that's 1. Let's not forget to take away the cosine x, and everything comes together now. The 1 minus cosine x's cancel out to 1. We get 1 over sine x, which is cosecant x, and we erase that. And believe it or not, this is equal to this. Now, you have to be extremely clever to know to take the 1 over sine x and multiply by 1 that way. You're going to have to be amazingly clever. But that's what you would do. If you have this, multiply the top and the bottom, that is this, by 1 minus cosine x times 1 minus cosine x. And that is this, because the sine squared minus the negative cosine squared, that's the 1, minus cosine x. I didn't change the numerator. Changed the way it looks, but I didn't change it. Okay, and if you divide this by this bottom, you just get what's in here. If you divide this fraction by first factoring out a cosine x, you're going to get cosine x over sine x, which I have here, and that became cotangent x. But you can always do it both ways. Next problem. Tangent squared x minus cotangent x, cotangent squared x, is equal to secant squared x minus cosecant squared x. Well, they're both the difference of squares. One side is squaring tangent x and cotangent x, which isn't sine or cosine. And the right-hand side is squaring secant x and cosecant x, none of which is sine or cosine. So that's a bit of, so we have symmetry there. I can convert the left-hand side to sines and cosines. Just remember that this right side is 1 over cosine squared x minus cosecant is 1 over sine squared x. If I can get this, then I say it's that. Okay, so tangent squared x minus cotangent x. Maybe I'll do the difference of squares right away. This is tangent x plus cotangent x times tangent x minus cotangent x. And tangent x is sine x over cosine x plus cotangent x is just a reciprocal times tangent x is still sine x over cosine x minus cotangent x is cosine x over sine x. Okay, I would get common denominators, which will be sine x, cosine x. We multiply the top by sine x, and over here, cosine x. Same thing here. Top and bottom by sine x, top and bottom by cosine x. And let's see what this gives us. For the first bracket, we have a common denominator. It's sine x, cosine x. The numerator is sine x times sine x plus cosine x times cosine x. That is, the numerator is 1. Times the bottom, sine x, cosine x. We are subtracting, keep the common denominator. And here we get sine squared x minus cosine squared x. Like I said, so the denominator is going to be sine squared x, cosine squared x. Because you multiply them, and you get sine squared x, cosine squared x. The first numerator is 1. The second numerator is sine squared x minus cosine squared x. That is, you don't need that 1 in the front. You get this minus that over sine x squared cosine squared x. Now, I would divide those two first. Sine squared x over sine squared x cosine squared x minus, then I subtract the other fraction. And nice things happen here. Sine squared x over Sine squared x is 1. So we get 1 over cosine squared x minus, this cancels out to 1. We get 1 over sine squared x. But like I said at the beginning, that is secant squared x minus, and that is cosecant squared x. Got it. Okay, so I got this first, and immediately I called it that. Make our teacher happy, erase that. That is that one. Let's do one more. Suppose you have 1 plus sine x over 1 minus sine x, and you want to show that this is tan x plus secant x squared. It's not easy to show that a fraction is something squared. But I can square the right side, and I see fractions like that's sine over cosine, that's 1 over cosine. Let's see what happens. So we have tan x plus secant x squared. So I get the first squared plus 2 times the product of the two things being added plus the second one squared. Okay, tan squared x is, well, tan x is sine x over cosine x. So if you have tan squared x, you have that, plus 2 times tan x is sine x over cosine x times secant, that's 1 over cosine x. Well, what I like about that is both denominators are cosine squared x, plus look at this, secant squared x is 1 over cosine x squared. Wonderful. Everything, remember, cosine x times cosine x is cosine squared x. All 3 fractions have the same denominator. And the numerator is sine squared x. 2 sine x times 1 is just 2 sine x plus 1. Now, just want to write it down over here. I want this to look like what I just wrote. Then I start to think. This denominator is 1 minus sine squared x, and that's the difference of squares. That's 1 minus sine x. Ooh, that's what I want. Times 1 plus sine x, which is something I don't want. 1 plus sine x. So, how is this going to become just 1 minus sine x on the bottom and 1 plus sine x on the top? Well, I have the bottom, that's good. So I want to get rid of this, no problem. I'll multiply by 1 plus sine x, and those cancel, and I get 1 minus sine x on the bottom. But I want 1 plus sine x on the top. Okay, I'll put another 1 plus sine x on the top. That is, this here, sine squared x plus 2 sine x plus 1 is 1 plus sine x squared. And we can do that in 2 ways. If I let u equal sine x, then that's u squared plus 2 times u plus 1. So it's going to be u followed by a number times u followed by a number. The 2 numbers should multiply out to 1, and add up the 2. You know what? 1 and 1 will do that. So I get u plus 1 squared. Oh yeah. U was sine x. So I get sine x plus 1 squared. Which is basically what I wrote here. If you didn't want to make the u substitution, you can realize that sine squared x plus 2 sine x plus 1, this is a polynomial in sine x. So we're going to have sine x followed by a number, sine x followed by a number. The two numbers should multiply out to 1 and add up to 2, and the numbers are both 1, which is 1 plus sine x, if I commute it, squared. Okay. Again, what happened is one of these sine squared x's in the top, okay, kill off one of the sine, 1 plus sine x is in the bottom. Since I had 2 in the top and I killed off 1, I have 1 left. There it is. And this is exactly what we set out to show. And that completes this video entitled Trigonometric Identities. Very long video. Look how many problems we did.